Welcome to my channel RLD Academy. This is lecture number 2 in transient analysis of networks. In this video, I'll give you a brief introduction about inductor, and then we'll try to find out the initial and steady state values of current or voltage in resistance inductor networks. Now, this is one picture of practical inductors. So you see, inductors are nothing but coils of conductors. So in this coil, you will find magnetic field whenever one DC source or AC source is applied. So we'll not go into detail in that process. So in this course, we'll try to use inductor as a circuit element, and we'll try to develop that knowledge, how to analyze the circuit with inductors. Now, this is the symbol we'll use for inductor, one coil, and its unit is Henry. Capital H will use in short, and the voltage developed across the inductor that will consider as V sub L, and inductor current I sub L. And inductance generally it is written as capital L. Okay. Now, so here I want to discuss one thing, that in this video we'll just introduce inductors in the circuit, and we'll develop the full concept about the inductors in some other future videos. Here just we will try to find out initial and final values. In transient phase or transient analysis will not be discussed here. It will be discussed later. So we'll discuss RL circuit in detail in some videos. There we'll find the equations related to charging or discharging of inductors. Okay, the transient analysis will be discussed there. Now, so you see the motivation for this video. In this video, we'll try to develop one concept to analyze this kind of circuit. Just look at the circuit. This is one source, 10 volt, and it's 1 ohm. Here it is 5 volt, 2 ohm. And here there is a switch, and this switch is, suppose it is closed at t equal to 0. It is closed. Okay, it is switched from this point to this point. Means suppose earlier it was connected to A, now it is connected to B at t equal to 0. Right? So here inductor is 1 Henry. You need to find out these values, that IL at 0 plus and IL at infinity, and DIL dt, the change in current IL, the rate of change in current at t equal to 0 plus. So this three quantity we want to find out, but again I'm saying that we'll not develop any equation, transient equations, all those things. Just from basic concept we'll try to find the answer. Okay, let us start. So you see, the last video I discussed the analysis with capacitor. Okay, initial and final values in a circuit, if circuit is containing k capacitor, one capacitor. So we'll try to compare these two, the effect of inductor and capacitor side by side, and try to understand this one. Right? So the capacitor you see we have considered like this. This is your capacitor. So this symbol sometimes I'll consider this kind of bending, but remember there is no difference between these two plates. So I'm not considering anyone is positive, negative. So any direction we can apply the voltage. But this kind of shape generally I'll use to avoid the confusion about the DC sources. Okay. Now this capacitance is C and its voltage across this one is VC, V sub C, and current is I sub C. The relation we got that IC equals to C dVc dt. So this is the fundamental relation. Okay. And very similar thing we will get for the inductor. Now for the inductor, this is one inductor with inductance L, and the voltage across this one is V sub L and current is IL. So here you will get different equation, just opposite one. Here earlier IC is C dVc dt. Now here VL is proportional to derivative of IL. Okay, so L DIL dt. Whenever there is a change in current, then voltage will develop across the inductor. Okay, so this is important concept, these two. Now from here we develop certain concepts. So in capacitor you see that for practical circuit I have said that all the quantities IC, VC, those are finite. Okay, so if you assume that all the values, the current and voltage in a circuit are finite, then we have said that this VCT in capacitor is always a continuous function. So this is one continuous function. Okay, continuous variable. That's all. Means if there is any change in a circuit suddenly, then also the capacitor voltage will not change suddenly. It is continuous. But remember that IC can change suddenly. ICT may change, may have discontinuities. Okay, means that it can change suddenly from one value to other value, right? So this is important, and this concept is useful for switching problems. So if circuit is changed, okay, if there is sudden change at t equals to suppose capital T, a switching is occurring. Okay, the switch. Okay, then you will see that VC T at T equal to capital T minus what was the voltage level, and it will be the same at VC at T equals to T plus. Just after, it is before switching, this one is before switching, okay, and this is your after switching. Okay, but remember that ICT can have certain changes. So this kind of lessons will not hold for current. So you can't use that ICT at T equals to T minus, it's the same as IC T equal to T plus. No. that is not valid. But Vc at t equal to t minus, it should be same as Vc t equal to t plus. Okay, so this reason we can use it for switching purpose. So for inductor, it is just reverse. So what you will find here, what is the logic behind here? So I am saying that in a practical circuit, all the quantity will remain finite. So VL and IL both are finite. So if VL is finite, then you see DIL dt, this derivative is finite. And derivative finite means IL is continuous variable. Okay, so here IL is a continuous variable. Okay, so it can't change suddenly. However, the VL, so I can write IL of t, and VL of t, it can change suddenly. Whenever there will be some switching in a circuit, so its value can jump from one value to other value. But ILT can't have that kind of jumping. Okay. So what I want to mean that if there is a switching operation at t equal to t, capital T, that time switching is there. That time I can safely use IL t equals to t minus whatever what was the current before switching, that should be same as the current after switching, t equal to t plus, at that moment only. Okay, so this will help us to solve the problems related to switching at switching moment, right? Then I said that in capacitors we can find the initial values, some initial state. Okay, at initial state, so if I assume that initial means at t equal to 0, when just circuit is starting, okay, circuit starts working. So the capacitor, if we assume that it is a relaxed capacitor, for relaxed capacitor, this word meaning that initially capacitor voltage was 0. So it's imply that the VCT at t equal to 0, it is 0 volt. There is no stored voltage across the capacitor initially. If there is no voltage across the capacitor initially, then what you can consider, the 2 point we can consider short circuit. So capacitor can, in that case, the capacitor is replaced by short circuit. That is the important concept, because voltage 0 means short circuit, correct? And the final one, if we consider final means the circuit is working for a long time. So I can consider that at t tends to infinity. That time, so capacitor is either fully charged, okay, or fully discharged, whatever it is. Okay, so at steady state, you will see the parameters, all the parameters will become constant, and this is obviously it is for DC circuits. So I am considering for this, all those things are for DC circuit. Means in the circuit, the source voltage or current, it is a DC, constant voltage. In that case, we can assume that IC and VC will remain constant. So you see IC equal to C dVc dt. So if VC is constant, then what is happening? IC will become 0 because derivative of VC is becoming 0. That imply the IC will become 0 at final stage. Okay. So this at finally I can write the IC at infinity. It will be 0. That is sure. And if current is 0, that we can consider as open circuit. So capacitor can be considered as open circuit. So what we'll do? So replace capacitor by open circuit. So this is important, right? So in the same way, the inductor is just opposite. So initially, the inductor can be considered as, there is no current, so relaxed inductor. That will imply that the IL0 is 0. There is no current, 0 ampere. So if current is 0, so we can consider as an open circuit. So this is as open circuit. Okay, we'll remove the inductor to analyze at the initial stage. And final stage means that t tends to infinity. So you will see the relation VL equals to L DIL dt. So if IL is constant, then derivative of IL is 0. So VL will become 0. So finally what will happen? The VL at infinity will become 0 because of this fact that we are considering DC circuit. In DC circuit, all the parameters, current and voltage will become constant. So if IL is constant, derivative of IL, DIL dt is becoming 0, thus VL will become 0 at infinity. So VL 0 means voltage across the inductor 0. That imply that it is short circuit. So this will give you short circuit. Okay, so you should replace the inductor by its short circuit element if you want to analyze the RL circuit at steady state. Okay, so that is called steady state. Right? Now with this concept only, we'll try to solve those problems. Very simple. This is a very simple concept. I told you that. So briefly, I can say the capacitor, the relaxed capacitor initially behaves as short circuit, and finally it will behave as open circuit because it is fully charged. There is no current to the capacitor. But for inductor, initially current is 0, thus it is behaving as open circuit initially, but finally the voltage across the inductor is becoming 0, thus it will behave as short circuit under steady state. Okay, now let us move. So we will try to solve this problem, that problem I told you. Okay, we need to find out IL 0 plus, IL infinity, and DIL dt at t equal to 0 plus. Okay, so first I'll consider before switching. Okay, right. So before switching means what? The t is less than 0 because the switch is on from A to B, is replaced from A to B at t equal to 0. So when t is less than 0, t is negative, that time the switch was with the point A. Okay, so that time what was the circuit? So we will draw the circuit only. So I can remove this one because this circuit element is disconnected. Just we'll consider this circuit. Okay, we'll draw that one. Right. So this is the circuit. And this is your inductor. Right. So this is your 1 ohm. This is 4 ohm. This is 10 volt. And this one is 1 Henry. Now you can see this one t less than 0 means this t is from minus infinity to 0. So it's infinite duration. So this circuit was closed for infinite time starting from minus infinity and will come up to 0 level at t equal to 0. So now we can say that the inductor will be under steady state with this circuit. Okay, because this circuit was closed for a long time. So can I say that at t equals to 0 minus, if you want to analyze the circuit, then inductor there, what will happen? So this will be a steady state, no? In steady state, VL is becoming 0, so inductor will behave as short circuit. So we replace this inductor by short circuit. Okay, so let us see. So what will happen? So this 1 and 4 I can combine. 1 and 4 is the 5 ohm. So these two I can combine. This is this one. And this is the source, 10 volt. Now this end will make it shorted. Because at t equal to 0 minus, the inductor is acting as a steady state condition, right? Is now steady state condition. So we can consider it a short circuit element because voltage across the inductor is becoming 0, right? So what is the current right now? So this current IL, now easily I can find out what is the IL. So IL is simply 10 upon 5 equals to 2 ampere. So rather I should call it IL 0 minus is 2 ampere, right? Now you know that after switching also the IL will be continuous. So IL 0 minus should be same as IL 0 plus. So one solution is that whatever circuit it will be after switching doesn't matter. If some source is connected, okay, then IL 0 plus should be same as IL 0 minus, and IL 0 minus we have got this one, and this is your 2 ampere. So this one is done, right? Now we'll consider after switching. Okay, I'll consider after switching. Means the range will consider t more than 0. Okay, so can I draw the circuit? So in this time, we'll not consider this part. We'll consider only this one, 5 volt, 2 ohm, then connected to 4 ohm, and then 1 Henry is connected. This closed path. Okay. So this is your resistance, 2 ohm. Then the source is connected here. That is your 5 volt. And now this 4 ohm is connected here, and it is the inductor. Right. So you see here this inductor is 1 Henry, and this circuit will work up to infinity. So at t equal to infinity, I can again consider that inductor will behave as a short circuit element, because again it will reach to a steady state level and voltage across the inductor will become 0, right? But initial voltage just after switching, what is the voltage across this one, that we'll discuss after some time. Okay, now we'll try to find out this one IL infinity. Okay, so for this IL infinity, what we'll do, so let us consider the next one. So we'll consider at t equals to infinity particularly. Okay, what will happen, the circuit will be this one, it is 2 ohm, this is the source, then 4 ohm is connected, and the inductor will consider as short circuit element. Okay, so this is your IL. Okay, so what is this voltage is 5 volt. So you see IL infinity will be, this voltage is 5 and total resistance in the circuit is 2 plus 4 is 6. So 5 upon 6, that much ampere. That's all. So IL equals to, at infinity is 5 by 6. So this one is done. So we have already got IL 0 plus, that is equal to 2 ampere, and IL infinity, you see it is becoming 5 by 6 ampere. Right. Now this one, how to solve these things? Okay, so at t equal to 0 plus, that I need to consider t equals to 0 plus. That's all. So I told you that at t equal to 0 plus, just after switching, inductor current is continuous. Okay, IL 0 minus is same as IL 0 plus, and that was your 2 ampere, right? So this circuit is now this one. So this is your 5 volt source, this is your 2 ohm, it is your 4 ohm, and this is 1 Henry. So at t equal to 0 plus, we know that the current is 2 ampere. So that current is circulating here. So this current is 2 ampere at t equal to 0 plus. That is sure. But we don't know what is the voltage across the inductor. So that voltage we can find out at 0 plus using KVL. Now we can apply KVL. We can use KVL in this loop. So this 5 volt is the source minus voltage drop across this 2 ohm resistance, that is your I into R. So this is plus, this is minus. Okay, and again this is plus, this is minus, it's a drop, and this one also I have considered as a drop. Okay, so this 5 minus 2 times 2 I into R minus again across 4 ohm, current is 2 and resistance is 4, 2 into 4 minus VL 0 minus 0 plus, sorry, that will be equal to 0. This is KVL. So if you solve this one, what you will get, this VL 0 plus will be 5 minus, this is 4 minus 8. So that will give you minus 12, 5 minus 12 is minus 7. Okay. Now this VL 0 plus, I can consider VL is L DIL dt, L DIL dt at 0 plus. Okay, and that is yours minus 7. So DIL dt, and L is 1 Henry. So DIL dt at 0 plus will be minus 7 upon 1. So it is minus 7 only. That is ampere per second. So in this rate it is changing. So the current through the capacitor, through the inductor, the rate of change of current through the change of current inductor, that is your minus 7 ampere per second. So this negative sign indicates that it is decaying. So current is, or it is flowing opposite side, okay? Right. So you can sub. So this is the answer. So this value is minus 7 ampere per second. So we are done. So you see, with this simple concept, we can solve this kind of problems. Right? Now, I'll give you a simple homework. So you consider this circuit. And in this circuit, I have considered one switch. That switch will be on at t equal to 0. Okay. And I have not said anything about the inductor value is inductance is 2 Henry. This 2 ohm is 5 ohm. And remember that if nothing is said about the inductor, then consider inductor as a relaxed inductor. Means initial current to the inductor is 0. That you can assume it. Okay, if nothing is said. So with that information, can you solve this problem? Can you find out IL at infinity? Okay, and I1, this is the current I1 through 2 ohm resistance, that I1 at 0 plus and I1 at infinity. Okay, so how to find out these problems, how to solve these things? So that you'll think, and I hope you'll be able to solve it, and post your answers in the comment section. And if you have any doubt, then also you can ask me, you can send me email, or you can write in the comment section. I'll try to clarify your doubt. I hope you have enjoyed this video, and if you enjoy, then please give a like and share it with your friends so that everybody can watch this video. And if you have not yet subscribed my channel, you can subscribe my channel. It is a free subscription, and for that you can press the subscription button, and then don't forget to press bell button, because then only you will get immediate notification of my future videos. So I hope you are going to subscribe my channel if it is not done yet. Keep watching my videos. I'll be uploading lots of videos in this channel, and hopefully I can help you. Thank you.